Okay, so continuing with our study of algebraic numbers and number fields, we're going to start looking towards defining some invariants of algebraic numbers. This is going to be the norm and the trace of an algebraic number. But before that, we need to talk a bit about something called the standard representation. So this is section 1.6 called the standard representation. What's this? So let's begin with a definition. So 1.6.1. Let K be a number field. And alpha be some element in K. Then to this element alpha, we can construct a linear map from it. A linear operator, something it's called. Then to alpha, we associate the linear map. I'm going to write A alpha, which is going to go from K to K, given by sending X to the element alpha times X. So it's just multiplication by alpha. Let me just note that by picking a basis for K over Q, we can write this as a matrix. In this case, we'll have rational coefficients, rational entries, because we're from K over Q. This map, alpha goes to A of alpha, is called the standard representation. And okay, in general, if I were working over K over F, then we can do a similar thing and write this as a matrix, but now with entries over F. So if I pick a basis for K over F, say some field in between, then this same thing works, but now I get a matrix defined over with entries in F. So let's do an example. I'm going to let K be Q square root 5 and alpha to be 3 plus 2 root 5. Then what's the basis for K over Q? So we have 1 and root 5 is a basis for K over Q. Right, every element can be written as A plus B root 5. So this is our basis. So alpha of 1, what's this? Well, this is 1 times alpha, which is 3 plus 2 root 5. And let's apply it to our basis vector. A alpha of root 5. This is alpha times root 5, which is 10 plus 3 root 5. And so in this basis, therefore, in basis we have as a matrix, this just looks like the matrix 3, 10, 2, 3. Right, I've taken my entries, my 2 and my 3, sorry, my 3 and my 2, put it in this column, and put this one in this column. There might be different conventions. Some people might put the 3 here, the 2 here. You know, might take this or the transpose. It's not going to make any difference for what we care about. So you won't lose any marks if you, instead of doing this, you had like the 2 here and the 10 here. That's fine. You can either this or the transpose. But I'll just use this one for now. Use this for now. So why are we looking at this map? Or what I call this thing a linear map. But I've not checked that it's linear, so let's prove some properties of this standard representation. So this is proposition 1.6.4. So again, K be a number field. and alpha some element of k. Then we have three things. The map alpha goes to A of alpha is injective. Two, if I let alpha and beta be in k and lambda some rational number, then A alpha beta is the same thing as A alpha times A beta. A alpha plus beta is the same thing as A alpha plus A beta, and A lambda alpha is the same thing as lambda A alpha. If you think of this as a matrix, and I just mean take the scalar matrix with just it's the diagonal matrix with lambdas on the diagonal times this matrix. So this part checks that it's a linear map, and this part actually checks that it works more there's not just a linear map, it has this multiplicative as well. And lastly, if C of alpha is the characteristic polynomial of A alpha, is the char poly of A alpha, then C alpha of alpha equals 0. So the characteristic polynomial of A alpha knows what alpha is. It has alpha as one of its roots. So this is our proposition, and it's not hard to prove, so let's prove this quickly. Proof. For one, we just need to note that so A alpha of 1 equals alpha. Therefore, if therefore we have alpha equals to beta if and only if A of alpha equals A of beta, because they both have to send 1 to the same thing. So this proves to me injectivity. 2 is obvious. This is clear if you remember that A alpha of x is defined to be alpha times x. So if you think of it in terms of what the map is, so then A alpha of x is alpha times x. So clearly A alpha beta of x is A alpha times A beta of x, and the same for all of these. So this is clear if you remember what the definition is. And for the third part, recall that we have this theorem of Cayley-Hamilton. So by Cayley-Hamilton, we know that a matrix satisfies its characteristic polynomial. So we know that C alpha of A of alpha equals 0. Just to remind us what this means, so you take a polynomial, C alpha, and then you plug in your matrix A alpha into it. And now this is some equation, but with some equation of matrices, and Cayley-Hamilton tells us that this is always 0. So now from 2, it follows that for any polynomial f in qx, we have f of A of alpha equals f of alpha. Just look at this statement here. So I can do multiplication and addition as it shows up. So if I have some polynomial, my scalars will pop out, and then I can just the rest will add and multiply as needed. So if I apply f to my matrix here, I guess this means take your polynomial in x. Everywhere you see an x, put an A alpha, and then you have some polynomial, some equation of matrices, and telling that these two matrices agree. So what we have is that A of C alpha of alpha This is the same as C alpha of A of alpha, which is 0. By this last equality is coming from Cayley Hamilton. This last equality is coming from Cayley Hamilton. Therefore, we must have C alpha of alpha equals 0 by 1, because we were assuming that our map was injective. So we know that this map A alpha to alpha is injective. So if some matrix A something is 0, then the only possibility for this thing to be is for it to be 0. And that completes this proof. So this standard representation is very, very useful later on for calculating or proving things about these norms and traces of elements, which we're going to define later on. But from this, I'm going to just make some definitions. This is definition 1.6.5. It says as follows, so let K be a number field. So you're going to get bored of me saying let K be a number field all the time, but I'll try and be as precise as possible. And alpha be some element in K. Then the characteristic polynomial of A of alpha, which we denoted C of alpha, is called, this has a name, this is called the field polynomial of alpha. It's called the field polynomial of alpha. We will denote it by C alpha, but note that this, if I were working, say, from over a field, so like K over F, then this polynomial would depends on what field you're working over. So if I'm working over the rational numbers, then I'm just going to write it C of alpha. But I'll say in general, we can define, say, A alpha of F and C alpha of F for alpha in K, and so K over F, an extension of number fields. So think of, you do the same definition that I've done, but when I define the map exactly the same, but when I go down to write down the matrices, I pick a basis over my field F instead of over the rational numbers. And then you get the same sort of thing. You get now matrices with coefficients in F, and you get characteristic polynomial, which now has entries in F, and so you get these matrices. So there is some dependence on over what field you're working on. But most of the time we're just going to be working over Q, so I'm not going to worry too much about it. Now, how does this field polynomial relate to the minimal polynomial that we talked about before? So here's a proposition, 1.6.6. So I'm going to let K be Q alpha for alpha some algebraic integer, algebraic number. Then C of alpha is the same thing as the minimal polynomial of alpha. So in words, the characteristic polynomial of A of alpha is the same thing as the minimal polynomial of my element. So the proof. Note that C of alpha is a monic polynomial. So characteristic polynomials are always monic. It's a monic polynomial of degree, this degree, K over Q, because A alpha is some matrix over the basis for K over F. Sorry, for K over Q. This basis is going to have this dimension. So it's going to be if this is n, it's going to be an n by n matrix. And so the characteristic polynomial of an n by n matrix is n. So this characteristic polynomial has to have this degree. And what we saw above, it has alpha as a root. So now we have two polynomials both of the same degree with alpha as a root. So this means it must be divisible by m alpha, because m alpha was taken to be the smallest polynomial, which has alpha as a root. But now we have two polynomials, both harmonic of the same degree, and one divides the other, so they must be equal. The monic bit tells you that there can't be any scalars, so one can't be like twice the other one or something, and they literally have to be exactly the same. This must be divisible by m alpha, therefore, as they are harmonic of same degree, they must be equal. And that's that. So if you want to find a minimal polynomial for some element alpha, if you're struggling to do this, you could write down the standard representation. So you could do what we did in this exercise over here, and then you just compute the characteristic polynomial of this matrix, and that will give you the minimal polynomial. So let's study this field polynomial a little bit further. So here's proposition 1.6.7. Like k be a number field, and beta some element of k. Not sure why I swapped from alpha to beta, but I did it in the notes, so I'm going to stick to it. Then a beta is diagonalizable over the complex numbers. This means, remember that, so this is some matrix. That means that I can find some bases under which this matrix is now some diagonal matrix. So it just has entries along the diagonal. And moreover, we have, and C of beta can be written as a product over I. So some polynomial, this is x minus sigma I of beta, where sigma I are all the embeddings of k into the complex number. So my my characteristic polynomial over the complex numbers is going to factor like this, where it's going to basically factor over all the embeddings of my root beta, which I remember, if you remember this, these were all the conjugates of beta. So let's prove this. This is a funny result, but it'll actually be quite useful for us later on. So by the primitive element theorem, which was 1.5.11, we can write k looks like some q of alpha for some alpha, some limiting k. So told us. Now by proposition, the previous proposition 1.6.6, we know C of alpha is the same thing as the minimal polynomial of alpha. And by proposition 1.5.6, we know that m of alpha is the same thing as the product over I of x minus sigma I of beta. We said that we talked about this proposition. Remember telling us that we knew that the element, the sigma I, has to send a beta to one of its conjugate roots, and a conjugate root is another root of the same minimal polynomial. So the minimal polynomial splits as a product of different roots, of different conjugate roots, and each conjugate root can be found by, is going to correspond to some embedding. So we have this, therefore C alpha has this many, so k over q, distinct roots, let me call this n, has distinct roots. This is this distinct, this is by lemma, by a separability lemma. Therefore, so you have a matrix whose characteristic polynomial has n distinct roots. It's an n by n matrix whose characteristic polynomial has n distinct roots. Therefore, A of alpha is diagonalizable. Over the complex numbers, and its eigenvalues are going to be the other roots of the minimal polynomial of the characteristic polynomial, which in this case is the minimal polynomial, which are the conjugate roots. So with eigenvalues being the conjugates of alpha. So what does this mean? That our matrix is diagonalizable, so we can find some matrix, say P over the complex numbers, such that so the following, such that we have P inverse A alpha P. This is meant to be diagonal, so this has to look like it's diagonal, and it's going to have the eigenvalues along the diagonal. Going to have alpha 1, alpha n, sorry, sigma 1 of alpha, sigma n alpha, zeros below, so it's going to look like a matrix like this. So this is what a conjugate of A of alpha, but you remember that the element that I was taking, that my proof was about this element beta, and so far I've only done, used the primitive element to write my field K as Q alpha, and then I've been telling you something about Q alpha. So now I've got to use this to say something about A beta. So how do we get back to the element that we care about? So now beta is some element in K, so we can find some polynomial, some f in Q of x, such that f of alpha equals beta. Just remember that Q alpha, these things look like A0 plus A1 alpha plus AN alpha to the n. So this is what these AIs are in Q. Once we pick a basis as sets, this is what things look like. And beta is some element of K, which is Q alpha. So beta is some element which can be written like this. So take this and make a polynomial out of it. So this is your polynomial such that f of alpha equals beta. No, just say note. Maybe this. We have this. So we have p to the minus 1 a beta p. This is the same thing as p to the minus 1 a of alpha f of alpha p. Now we're going to start using the that beta is the same thing as f of alpha. We start using the previous proposition that two propositions ago. This is the same thing as p to the minus 1 f of a alpha of p, which is the same thing as f p inverse a alpha of p, which equals, if you look at what our matrix looks like here, this just looks like f of sigma 1 of alpha, f sigma n of alpha. You have zeros outside of that, outside of the diagonal, and now this is just think of what this has to be. This is just going to be sigma 1 of beta, sigma n of beta. And like this. I'm taking my polynomial. Now I apply sigma to this. So alpha is going to map to one of its conjugate roots. Beta is going to map to one of its conjugate roots. And so this is what this thing turns into this. Now we're done since P inverse A beta P and A beta, both of these things, these are conjugate matrices, so they have the same characteristic polynomial. Now since this have the same char poly as their conjugates, they are conjugate matrices, we get the result. Great. So we can prove that for any beta that we get, I can always find a change of basis, which will make my matrix diagonalizable, and my characteristic polynomial will just split as product of all over all the conjugate roots of my element. So here's a useful corollary of this. So corollary 1.6.8. So let K be a number field. And beta some element in K. Then C beta of X, so this characteristic polynomial, is the same thing as the minimal polynomial of beta to the X to some power, and the power is the degree of K over Q beta. Which is this again, this is some polynomial in Q of X. So what is this saying? Remember that up here we said that where was it? We said that if I had an element alpha, if K was Q alpha, then the characteristic polynomial alpha looked like the minimal polynomial of alpha. But now in full generality, if I just take some element K, it doesn't have to look like Q alpha, and I try and figure out what it is. Well, this characteristic polynomial, the field polynomial, is going to be the minimal polynomial to some explicit degree. And this is some polynomial over the rational numbers, which might not be obvious. Well, it's obvious if you look at it like this, but if you look at this, what the field polynomial is in terms of this product of all the embeddings that we have here, then it might not be clear that this thing is always a rational polynomial, a polynomial with rational entries. So how do we prove this? So first of all, by proposition 1.6.7, we know all the roots of C beta are of the form of sigma I of beta. So we just proved. Now I'm gonna let A to I be the embeddings of this field, the field that you get by adjoining beta. Then by proposition 1.5.8, we know that each of these is going to extend to an embedding of the full field K. In how many ways? Well, the number of ways it's going to be this number here, K to Q beta. So we know that each A to I extends to K to Q beta embeddings of K into C. So when you extend the embedding, it means that the new embedding, if you restrict back down to K beta, they agree. So these embeddings all keep all of these setting inventions keep nu I of beta the same. Right, because this is what it means to extend an embedding. So for each eta I, there exists k to q beta, this number of embeddings sigma j, which go from k to c, such that sigma j of beta is the same thing as eta I of beta. So yeah, I'm just saying that a lot of this is a product of overall all the different embeddings of beta. This is x minus all the product of all the different embeddings of beta. I'm saying that a lot of those sigma i's just do the same thing to beta. They all act exactly the same. And this is from this extension result, that if I have an embedding of this field, then it extends in this many number of ways. So if this number was 3, then for every embedding of q beta, I get 3 embeddings of k, which when restricted back down agree with my original one. So for example, in this case, I'd get 3 of these for every one of these. So in this product, you're going to get lots of repetition, and this is what we're showing up. So we have this sort of thing. Now, since minimal polynomial of beta of x equals product over I of x minus eta I beta, by definition of what minimal polynomial is, we see that c of beta of x has to be the following: is product over I x minus eta I of beta. We have this thing all to take account for the repetitions. And we have it this many times, this giving the result. One thing to note is that, so I'm trying to note that. So we know that this degree, this is the same thing as, by a Tower law, we know that this is the same thing as the degree to k beta, and then from k beta down to q, sorry, from q beta down to q. So the power that we get is correct. Since we saw above that C alpha has degree, C beta has degree k to q beta, and m alpha has degree, m beta has degree q. So this thing has degree k over q. This matrix m beta has this degree, and so this is m beta. So if I take m beta and raise it to this power, the degrees match up correctly. Okay, so this is where we're going to leave it for standard representations and field polynomials. But this result is going to be quite useful later on, this corollary. But we're going to, in the next lecture, we'll use this to define the normal trace. But I'll leave this here.